Yeah, so firstly, thank you, a big thank you to the organizers for inviting me here. I've really had a really wonderful time at this conference, getting acquainted with the gravity community here. So I'll be talking about some recent work I've been doing. Mostly I work on structure formation, but I'm interested in understanding the connection between the evolution of galaxies and dark matter halos in the universe and the binary compact object population that are basically the sources of gravitational waves that we see today. And basically what we can learn from the interconnection, what we can learn about the underlying models, underlying formation channels of these binary systems from our knowledge of galaxy formation and structure formation, and vice versa, what we can learn about maybe structure formation from these events. Of course, gravitational waves have really opened up a new window into the universe, right? We've been observing our sky in a variety of wavelengths, right? In a variety of different probes, which basically probe different astrophysical processes in the universe. And now, as over the past in the last few years, and starting from the first detection of gravitational waves in 2015, we have slowly started to build up a map of our sky in gravitational waves, right? Essentially, we've started to map our universe in gravitational waves. Currently, we're in these first generation of detectors. We're really talking about the LIGO-Virgo detectors, which are ground-based interferometers, and they are mainly detecting these stellar mass binaries that have high wave frequencies, essentially. So we are looking. So far, we have sensors of binary neutron stars, binary black holes, and neutron star black hole mergers, right? So just flashing a plot from the LIGO-Virgo collaboration, just from the O1 run, moving on to the O2, O3 run, we are really building up this census of all these really interesting objects, interesting astrophysical objects in the universe, right? So this is the plot that has been basically flashed several times in this conference. Of course, the masses in the stellar graveyard, as it's called, or maybe the masses in stellar afterlife, however you want to think about it. And here are all the gravitational wave detections, and these are the electromagnetic detections of these binary black hole and neutron star systems that we've had so far. So what we're seeing, as we're getting more and more events over the past few years, what we're really learning is that there are all kinds of diverse and very interesting inhabitants in our universe, right? Which really make living in this universe quite an interesting thing, right? So we have, of course, GW 170817, which was the first gravitational waves, which was the gravitational wave detection, which had an electromagnetic counterpart, which was very exciting. It gave us the first, it had many implications, both for cosmology and for astrophysics. Then we had all these interesting events. Yesterday we heard about the final black hole mass being in the intermediate black hole mass range, and the progenitor masses essentially being in the parent stability mass gap. So all these kinds of interesting things, interesting astrophysical objects are being revealed as we go ahead in this endeavor, right? So even if we take the basic things that we've learned many things, but if we were to summarize some of the basic things basic profound things that we have learned already from these discoveries, really we can summarize at least some of the most exciting things and some of the most profound things that we have found out about here, right? I won't go through all of them in the interest of time. Actually, I might exceed, so I'll probably get to the crux of my talk. All right, so given that we are looking at all these diverse events, it's important to understand how these systems actually form and how they evolve through time, right? So these binary systems, at least in the most vanilla model, particularly the black hole binaries or the binary neutron stars, are essentially forming in the galaxies that we see in the universe, right? And we have, and they follow the evolution of this, in the most general sense, they follow, we can expect them if they're to follow sort of like the evolution of stars in the history of the universe, right? The evolution of baryonic matter or the evolution of galaxies in the history of the universe, and depending how exactly they form, they sort of are in a sense sort of like, you know, biased tracers of the star formation or the properties of the galaxies that we see that you know, basically trace the entire history of the universe. So in these first generation detectors, while we're, you know, currently we are somewhere around here in redshift, but in future, in the second and third generation of detectors, we'll actually be mapping out, in a sense, the evolution of these massive stars, right? Because these compact objects are usually formed from, binaries are formed from massive stars, we'll be mapping out the distribution of these massive stars, the cosmic star formation of these massive stars, if you might say, out to very large redshifts, right? So out to almost the dark ages of the universe, we are really going to see, hope to see gravitational wave signatures from binaries merging almost through the entire history of when we think we've had, you know, galaxy formation and star formation in the universe. So there's really, so you know, we apart from learning just about, you know, so this is essentially sort of giving us a different way to map out the entire cosmological evolution of star formation rate, right? And in principle, this is another way to understand structure formation, right? So we know that these binary systems should be embedded in the cosmic web, in the larger cosmic web that we see where our galaxies live and evolve in an underlying, so this is just a dark matter only simulation with galaxies populated with some semi-analytical models. Sorry, I forgot to add the citation. This is taken from the Wexler et al. Group. And this is the cosmic web of structure formation, and these nodes are essentially where we think dark matter halos form, within which these galaxies form, and within those galaxies are where these binary systems are forming and evolving, right? So of course, once we have enough data, or even once we have sufficient amount of data, we can start asking a lot of interesting questions about the cosmological evolution. Of course, we are all familiar with the fact that these binaries are, of course, an independent tracer of the cosmic expansion. So we can measure the Hubble constant, because these can be used as standard sirens. Of course, we want to understand what is the clustering of these objects, how do they cluster, what kind of galaxies do they live in, what are their overall clustering, can we measure different cosmological parameters, you know, other than the Hubble constant as well, using these binary systems. What kind of biased tracers are they of dark matter, what kind of tracers are they of their host galaxies, right? So these are from the cosmological perspective, and there are a wide range of other questions that people are looking into. And you know, you are only limited by your imagination of the things that you can ask and things that you can do with these events. And of course, at the astrophysical level, what I basically want to understand is how, once we put these binary systems in the context of the entire background structure formation, what do we understand about the intrinsic properties of these mergers, right, when we relate them to the galaxies with which they evolve? How do they form? How and when do they merge? Are these populations consistent with our understanding of massive stars and our understanding of general galaxy formation in the universe, right? So what I will be mostly talking about in the next part of my talk, is how do we use, once we have these events, and for a fraction of these events, we will have electromagnetic counterparts. For neutron star mergers, we expect to see them. And for a small fraction of the black hole events even, given we will have very small localization, but so that we might have some, there's some probability of actually isolating a host galaxy. So if we have a host galaxy, if we have a population of host galaxies for these systems, what can we learn about the underlying properties of these binary systems, right? And alternatively, by trying to understand the underlying properties of these binary systems, what kind of host galaxies should they live in, and how do those host galaxy populations, how do understanding those host galaxy populations, how do they bias our measurements of different cosmological parameters, and so on, right? So basically what I want to understand is the interplay between these host galaxies of the binary systems with their host galaxies. All right, so starting from the basics, so particularly for these neutron star or binary black hole or BNS, black hole and neutron star mergers, primarily there are two different channels of formation that people look at historically. One is the isolated scenario, where stars form in a gas cloud early in the evolution. They form as a binary pair, and they, one of them goes supernova, then the other goes supernova, and they merge to form a binary. So these are the isolated formation scenarios. These are expected to follow the overall star formation in the universe, right? So the fraction. So if we track the star formation history of a galaxy, the number of massive stars is a fraction of those star formations. So these isolated formation scenarios should essentially track the star formation properties of a galaxy. And then other than that, particularly for black holes, it's important for massive black hole mergers, the dynamical formation in dense clusters also becomes really, also could be important, in the sense that these, in dense clusters where you have massive black hole binaries, they will tend to sink to the center, mass segregate and sink to the center, and then they are often likely to be captured into binary orbits due to three-body interactions. So these then have a different, these don't necessarily then follow the star formation properties of a galaxy, but could follow in principle other galaxy properties which are related to the sort of number of dense clusters in there. But for neutron stars, it is, I think, widely thought that they are more likely to follow in, to fall in the category of being formed in these isolated formation channels. So let's go back to the events GW1708-17. So this was the gravitational wave event that we, this was an exciting gravitational wave event where not only did we detect the gravitational wave signal from the merger of the two neutron stars, it was basically detected in almost all across the electromagnetic spectrum, and we could identify kilonova associated with it, and we could identify the host galaxy in which it was lying. So the host galaxy of GW1708-17 was isolated to be this galaxy called NGC 4993. So this is basically where the event took place, and this is like a zoom in of that region. So what kind of a galaxy is the electromagnetic counterpart of GW1708-17? What kind of a galaxy is NGC 4993? So it's a galaxy which has a stellar mass of about 10 to the 11. So it's pretty, given the distribution of stellar masses that we see in the universe, it's a pretty massive galaxy, slightly higher stellar mass than our own Milky Way. The star formation rate of the galaxy is quite low. And the other things that we know is that this galaxy may be associated with a galaxy, is actually associated, it might be in the halo of another, it might be, it's associated with a galaxy group, which are thought to be bound together. And also we know that this is an elliptical, this is also a shell galaxy, and there's some interesting work saying that the merger actually took place in one of the shells within NGC 4993. All right, so these are all the properties of the galaxies. The one galaxy that we have, at least for the for the gravitational wave event. But we should remember that this is the property of the host galaxy when it merged, right? So this is the property of the host galaxy where the binary neutron star merged, right? However, these neutron star mergers, these neutron star mergers, or the binary black hole mergers, are often characterized with a delay time distribution, right? So these binaries, as soon as they form, they don't merge instantly, or they're not thought to merge instantly. There's usually a delay between the time when they form and the time when they end up merging, right? And it's often this delay time distribution, this delay between the formation of the stellar binary system and their final merger, is characterized by this kind of a power law distribution, where T is the merger time, and TD is some minimum delay time. So it can have delay times basically that fall off as a power law minus alpha, right? So this power law behavior is expected, it's often modeled as this power law behavior. This is expected based on the distribution of the orbits of which these Keplerian binary systems are produced, and that is expected to follow a power law, which then translates into this delay time distribution model, right? So now, if the delay time, so this delay between the formation of the binary and the eventual merger of the binary, if the time in between them is of cosmological time scales, right, of time scales of hundreds of million years, or is of the time scale of a gigayear or so, galaxy can significantly evolve in that time scale, right? So the galaxy in which the binary system was born can be significantly different from the galaxy in which the binary system will be merging. So then to get to that delay, so what we want to do is, how do we actually constrain these delay time distributions from the properties that we find of the galaxies in which they merge, right? Given the galaxies in which they merge, can we say something about how these binary systems had evolved based on what we know about how this galaxy has evolved in time, right? Primarily, there are two ways in which we can constrain this delay time distribution. One is the redshift. These are the two broad ways. One is the redshift evolution of the rate of binary mergers. If we think that these binaries are following the overall star formation in the universe, right? So how star forms, how many stars form at every redshift. There's a fraction of them that will form as massive stars. So we expect them to follow the, so this is the cosmic star formation rate density versus the redshift. So this is late times, so now versus early times. And this is the overall star formation history of the universe, so how the universe formed and accumulated stars through its history, right? So one way is using this method to see how the rate of, if we get the rate of binary mergers at every redshift, that will basically be just a shifted form of the star formation history, and that will help us then constrain these delay time parameters. And the other way is, instead of having the whole rate distribution over the entire redshift, we can actually look at snapshot properties of the galaxies and say something about how these delay time distributions evolve. So this is just the idea of the getting it from the merger rate distribution as a function of redshift. So if we have the cosmic star formation rate density, this is scaled by some number, then for different delay time models, for different slopes, for example, for that power law of the delay time distribution, you will essentially be shifted, and some minimum delay time after which you merge. You will essentially have a merger rate density which is shifted from the overall cosmic star formation rate density by that time. And this, this difference between the peak will essentially give you constraints on both the minimum delay time allowed, and also the slopes, the overall evolution of the slope will give you a picture of how this, what the power law slope of this distribution should be. So that's through the redshift distribution, but it's going to be a while before we get to that peak of, get to the redshift peak of that, of the binary black hole merger rate distributions. But we can also do better just by looking at the host galaxies that they live in, right? So as I was saying, binaries co-evolve with the structure in the universe. So you have some progenitor stellar system. They live in a galaxy that lives part probably of a larger galaxy group or a galaxy cluster, which lives as part of your entire distribution of galaxies in the sky. This galaxy's evolution is significantly affected by the environment of this galaxy's properties, particularly its star formation history, its stellar mass accumulation over its history, is affected by the overall cosmic environment in which it lives, right? And we have, given our understanding of optical and cosmology in all different wavelengths, we have now a very good statistical understanding of the connection between, it's called galaxy halo connection, or the connection between the galaxy properties and the overall evolution of the universe. So what we think in general is, how does a galaxy evolve over its history, right? This is the basic cartoon picture of it. So we think that a galaxy, an individual galaxy, right, starts off as some kind of a spiral blue star forming galaxy, and as it evolves through time, it accumulates stellar mass, it has gas accretion, it accumulates stellar mass, after which feedback processes start, and it starts to lose its star formation. Its star formation starts to quench rapidly, and then eventually over its time it will end up as some red elliptical galaxy. So basically, given how the galaxy evolves, depending on at what stage of that evolution history of the galaxy we catch the merger in, we have some idea of how that particular galaxy's star formation evolved over its history. So then we can say, at first order, and the simplest thing that we can do is we can say, suppose that if we find a galaxy host which is in some stage over here, and we have an idea of its star formation history, we can say that, okay, that galaxy formed most of its star at this redshift. So maybe the binary also likely formed at this redshift. So we'll get some estimate, quick estimate of how what is the delay between the star formation, some probabilistic estimate of what is the delay between the star formation and between the binary formation and its merger. So just to elaborate on this point, right? So essentially, what we have is so the star formation history of the universe is what we were talking about. So it's basically, the star formation history of the universe is found by just adding up all the stars that form in different galaxies at a given redshift, right? So this is the star formation history of the universe here, right? So I've flipped the sign around. So this is now late time, and this is early time. And this is your delay time distribution, right? So this is basically the power law distribution of delay times that we have. And so what we see, if we want to measure the delay time distribution at some given redshift, right? If you want to, so say when the age of the universe is about now, if we wanted to measure the delay times, it would essentially be just a convolution of the entire star formation history of the universe with this delay time distributions, right? So you have more mergers happening with short delay times and fewer mergers happening with long delay times. So you have more mergers coming in from this region, and fewer you expect probabilistically to be coming in from this earlier region. However, the star formation was much higher at that longer time scale. So that sort of ends up, so it's a balancing act between the higher star formation but the lower probability of forming mergers with that delay time. So what you essentially get is a convolution of these. So at any given redshift, if you were to look at the delay time distribution, you would get, particularly at late redshifts, you would get some kind of a delay time. So if you looked at all the mergers that you're getting at redshift today, and if they had some kind of a clock attached to themselves, you would see that this was essentially the distribution of their delay times. At different redshifts, this distribution will change depending on which part of the cosmic star formation history contributes. However, to cut the long story short, what is important to note is that at any given redshift, if you have short delay times, if the binaries merge as soon as they form, they are likely to live in star forming galaxies, right? So these galaxies have constant star formation. There's a lot of new blue stars that are being formed. They are instantly forming, and if they merge instantly, you will see that these short delay time objects will be placed in these, you'll find a lot of these mergers having host galaxies that are blue and spiral. And you'll find a smaller fraction of, but you will find some fraction because there is a tail at longer delay time. And there's a lot of stellar mass in these bright elliptical galaxies. So you will also find a tail for the long delay times in these bright red galaxies. So these are called red and dead elliptical galaxies, even though they look yellow here. So I might often refer to them as red. Right, so for longer delay times then, you're more likely to be in an elliptical red galaxy. For an elliptical red galaxy, the star formation history looks something like this. It formed most of its stars at a much earlier time. So these things are merging today, so they'll have long delay times. Whereas for a spiral galaxy, the star formation history it's still rising. It's still in the star formation stage. So it has a lot of recent star formation. And you are mostly probing with these galaxies the shorter delay time objects. All right, so to summarize them in this mathematical form, essentially the merger rate of a galaxy, the current merger rate of a galaxy is just the convolution of the delay time distribution and its own star formation history, right? So one particular galaxy has formed stars over its lifetime in a certain way, and you're embedding upon it the delay time distribution of binary mergers. And then, so that's the rate of one galaxy. But when you want to look at the distribution of galaxy properties, right? So if you had many different mergers and you wanted to see what is the distribution of, say, the stellar mass of the galaxy, for example, of the galaxies in which you find these mergers, that distribution then again has to be scaled not only by the rate of that, it has to be the rate scaled by basically the luminosity function of galaxies in the universe, right? How many galaxies do you actually, how much of your star formation actually takes place in galaxies of say M star, a particular stellar mass galaxy. And that luminosity function of galaxies is of course intrinsically related to structure formation, we think, which basically depends on your halo mass function, right? What's relating them is of course the stellar mass to halo mass relationship in the universe. So what stellar mass galaxies live in what halo mass, and how the distribution of the halo mass function evolves with time essentially sets this relationship. All right, so we can try to track that analytically with like a Preshekta kind of formalism and using some analytic models for the stellar mass halo mass relation. Or we can use a dark matter only simulation, we can use a full cosmological simulation which has not only, which has the whole structure formation incorporated in it. So one of the things that I've been working on is to incorporate, is to take our structure formation simulations and basically these structure formation simulations give us the entire history of how halos evolve through time and how structure evolves through time, And you can, without doing the full hydro, which can often be quite challenging, you can use semi-analytical models of galaxy formation to populate the structure with galaxies, and then you can go a step ahead and actually use the semi-analytical model galaxy formation and their galaxy formation history to embed in them binary populations, right? So you can actually start from these cosmological simulations and populate them with binary mergers to study sort of the statistical distributions of host properties of different delay time, underlying delay time distributions of these objects. So I am mostly working with these universe machine simulations, which were developed by Peter Beruzzi. So this is a semi-analytical galaxy formation simulation, which just takes a dark matter only simulation. It's a gigaparsec, this particular one is a 250 megaparsec volume, cube volume, and it basically has a semi-empirical model that parameterizes the correlation between the star formation rate of a galaxy and the properties of its parent halos. It basically says that the rate at which a galaxy forms stars is, and its stellar mass increases, is related to the rate at which the halo forms, builds up its mass, and it parameterizes that relation and tries to constrain it basically using like a wide set of observables. So what it provides is, it provides entire merger histories of galaxies. So you have some red elliptical galaxies, you have the entire merger, and we look at this all the time in simulations, you have the entire merger history of that object in the universe, and now you also have the entire galaxy star formation history, and it basically provides a catalog of galaxies with its stellar mass, its star formation rate properties, and all different kinds of properties, along with, of course, any cosmological local density clustering properties of galaxies that are naturally embedded in a cosmological simulation. So we populate these simulations. So now what we do is we take the star formation history of each of these galaxies and we populate them with a delay time distribution, right? So we say that, okay, so we take these galaxies which have a distribution of star formation rate, we populate that star formation rate with the delay time distribution, and every galaxy's star formation history then predicts for it merger rate at every redshift, right? So we have basically the entire evolution of the merger rate for a single galaxy and for the entire population distribution of these properties, right? So given an input delay time parameter set, we have all kinds of output host properties that we should see at a given redshift. Right, so then for different delay time models, we basically see where the galaxies should lie. So this is the stellar mass star formation rate plane. So we take a short delay time of, for example, if we have a very short delay time, which is sort of less than a gigayear, what we'll find is that in the stellar mass specific star formation rate plane, our galaxies will tend to lie in the star forming arm. Okay, and this is the, so this is high, at every mass, these are the most star forming galaxies. So the color is basically, the density of objects in that, density of mergers in that stellar mass star formation rate bin. And this arrow over here, or this point over here is basically where NGC 4993 is. Then we also, this is what happens for a long delay time. You can basically map out where the host galaxies of these long delay time mergers should be, and as you can see that the peak shifts to higher stellar masses, because high stellar mass galaxies, so this is all at redshift 0. High stellar mass galaxies today actually formed most of their stars earlier around redshift 1.52. Right, so then you can basically, for different delay time models, sort of try to map out what these distributions should be. Not only the distributions of the stellar mass and star formation rate, you can also map out what should be the, for example, the local density at which you would find these galaxies, right? So this is the density at, this is basically, this is sort of a contrived parameter of the nearby density to a larger volume density, but essentially it tells you that, you know, for these, for things which with long delay times, they tend to lie in more massive, not only galaxies, they also tend to lie in more massive halos, and therefore they are more biased as well. They are more, they live in dense environments as well, so you will find that these have all kinds of cosmological implications for the clustering properties of these objects. And similarly, you can also find what kind of halo masses and velocity dispersion of their nearby groups that they live in looks like. All right, so now that we have a way of changing our parameters and therefore getting a stellar mass, a galaxy property distribution, we basically try to estimate how many events do we need to start constraining these, the slope and the minimum delay time parameter for these merger models. And, you know, essentially we found that, you know, of order, so you can, with order of 100 events, you should be able to start constraining this alpha slope quite well. It's significantly, the delay times you can constrain quite well. The alpha parameter is harder to constrain. Right, so then we ask simple questions. I'll skip over that just by asking just simple questions. You know, you can just use orders of 10 galaxies, 10 events to just rule out very simple basic questions like, do the mergers follow stellar mass, or do they follow star formation rate? Do they follow galaxy halo mass, which is the case for globular cluster formation? So you need of order 10 to 30 events with electromagnetic counterparts to start telling the difference between these models. And finally, you know, you can get these, you can get the overall distribution. So this is a 250 megaparsec volume, and these are where all the mergers should lie if you were to see them. So this is sort of your gravitational wave sky. So if you have short delay times, they're a lot less clustered, whereas if you have long delay times, you'll see that there's a lot of mergers coming in from very clustered regions of the universe. So the clustering depends intimately on these long and short delay times. I guess in the final part, I just want to talk about a slightly different thing. And I wanted to point out that, you know, we have one event from gravitational waves with an electromagnetic counterpart for binary neutron stars. But, you know, we've been looking at short GRBs. We have GRBs for a much longer time, right? And there is some consensus that we think that short GRBs actually come from binary neutron star mergers. So so recently for the short GRBs, we have where we have identified hosts, where we can actually identify associated with the host galaxy. We use those galaxy samples to actually make some first test of this method that we have of basically constraining these delay time models using the entire star formation history of the galaxy. We used this GRB host catalog that was recently published by Wenfei Fong's group, which took basically photometric and spectroscopic images of GRBs with identified host galaxies, and also HST follow-up to see deep HST follow-up. And they have a total of sort of 66 candidates with host galaxy associations. And these host galaxies, some of them actually have the spectroscopic and photometric data from which we can actually construct star formation histories for these individual galaxies. And we can populate that with these delay time distributions and try to actually constrain the delay time distributions directly from these short GRB host galaxies. So we used the sample of 66 galaxies, and we found that it appears that there's a minimum delay time of around 200 million years, and the slope of the delay time distribution is about minus 1.83 plus minus 0.4 approximately. So this is interesting because these slopes are expected to be either in the -1 range or in the -1.5-ish range if there's common envelope evolution. So we tend to find the slope to be pretty high. But we actually have the first constraints. These are the first constraints from host galaxies for the underlying delay time distributions for binary neutron star mergers. So that actually predicts a rate of this, of the binary neutron star mergers, which we should actually expect to see in LIGO. So it'll be interesting going ahead, comparing what we get from LIGO to what we get from just the short GRB host galaxies. And finally, you can study about all kinds of interesting properties of these galaxies. You can take these parameters that you've established and populate simulations and actually make your GW skies and do all kinds of analysis with them. Currently, there are some intriguing differences that we are finding when we populate the galaxies with the constrained simulations with the constrained delay time distributions. But in principle, that's telling us in a way of what we understand about galaxy formation as well. So I'll stop here. The future is quite exciting. We are starting to build a census of these binary systems, and we can relate them to their host galaxies and do all kinds of fun things with them. And yeah, thank you. I'll stop here.
Thank you, Dr. Adhikari, for this talk. Couple of questions. Can someone put on the light, please? That's my pleasure. Otherwise, everything looks like dark.
So my question is, so you are doing a dark matter only simulation. I'm here.
Yes, hi.
So you are only doing a dark matter only simulation,
yeah.
And then you are associating baryons or associating galaxies, and then how we know that how many mergers will be there in a galaxy? I mean.
Yeah. So there is a model there, right? So we have the full cosmological dark matter only simulation, from some redshift 99 to redshift 0, right? And we start with some initial density distribution. So we have, in the volume of 250 megaparsec, we have essentially you have all the halo mergers and, different halos merging into each other and different, through cosmic time, right? So now you have a model which basically relates the galaxy's star formation rate with the halo's mass accretion rate. And that model actually works very well, it has seen. So it is very successful in sort of producing the cosmic star formation history, the observed stellar mass, halo mass relationship. So it's an empirical model in that sense. So you relate the star formation history of the galaxy to the merger, to the mass accretion history of the halo. And that then gives you how, that incorporates the mergers of the galaxies itself. So every time you have a halo merging, you have some time scale after which the galaxies themselves will merge. And then you add up their stellar masses under some condition. So galaxy merger is included in this model. Yeah.
Hi, thanks for the nice talk. So you mentioned that with the 10 events with electromagnetic counterpart, you should be able to distinguish at least some of the formation channels and can constrain them.
Very basic question.
Yeah. So, but are there some comparative study, or can you say something about when we don't have electromagnetic counterparts and if we use the cross correlation between the galaxy catalogs and the GW events, how many events we can expect to have before we can put similar constraints on the formation channels without the electromagnetic counterparts?
Yeah, so that analysis is sort of to be done. Sort of Aditya is Vijay Kumar, who's a student at ICTS. He's kind of working on that based on these simulations. So you can vary your initial delay time distribution, and then you can make predictions for how the galaxy, say the GW cross galaxy cross correlation should be, or even the autocorrelation should be, and you can start making estimates of how many events you need to distinguish them, say, from cross correlation studies.
Okay, we have already entered into the tea time, so let me close it here session, and we can discuss with her during the tea or coffee. Okay, and thank you again, Dr. Adhikari, for the talk. and don't forget to take your phone.